I'm Major Rick Shows, a project officer for the F-18 program at the Naval Air Test Center. Today, we are going to discuss tactical aircraft icing. In the past, icing has not been considered a major concern for us in the fleet because of the durability of older aircraft models such as the F-4 Phantom. However, the advances in airframe and engine design make newer aircraft, such as the F-18 Hornet, much more susceptible to icing mishaps. For example, since the Phantom entered the fleet while I was in grade school, 7 icing mishaps have been reported, with only 3 resulting in limited engine damage. In comparison, the F-18 Hornet encountered 26 icing mishaps between combined Canadian and U.S. naval forces during the winter of 1984-85. All resulted in some type of engine damage. In this brief, you'll receive a refresher course in meteorological conditions related to icing and how and why icing can be a serious flight hazard, along with recommended procedures and techniques to reduce the possibility of an icing mishap. Lieutenant Jim McNitt, attached to the Naval Oceanography Command Detachment at Patuxent River, will present the meteorological portion. Mr. Brian Picard, a mechanical engineer with the Strike Aircraft Test Directorate, will present the engine and airframe technology portion. I will wrap it up with recommended flight procedures. At this time, I'd like to introduce Lieutenant McNitt.
I'm going to talk today about aircraft icing and how it affects you in tactical jets. Now, icing is the most hazardous weather-related factor involved in tactical jets. For example, an FA-18 making an IFR approach in NES Fallon, Nevada, encountered clouds at 2,000 feet and was clear at 1,000 feet with his engine anti-ice switch on, and after a minute and 10 seconds in the clouds, suffered ice-induced FOD damage on his port engine. Now clearly we have a problem here with our thinking in icing. If an airplane can be in clouds for that short of a period and encounter ice severe enough to FOD out an engine. Let's talk about the factors involved in aircraft icing. The first one is that the airframe surface temperature must be below 0 degrees Celsius. That means the amount of supercooling must exceed the amount of aerodynamic heating or skin friction on the aircraft. And the low subsonic airflow around aircraft, especially around the inlet ducts, will cause the freezing temperature to raise by as much as 2 degrees. The supercooled water droplets must also be present. Often supercooled water droplets are present in the form of clouds. Now, water droplets in the atmosphere usually freeze from -10 to -40 degrees Celsius. But when a supercooled water droplet hits the skin of an aircraft, then that internal stability is destroyed in the droplet and the freezing temperature is raised. 3 main types of icing we're concerned about in flight: rime, clear, and mixed. Rime icing is the instantaneous freezing of small spherical water droplets. Air bubbles are trapped between those spherical supercooled water droplets, and the ice becomes very brittle. It's a very slow accretion type ice compared to clear icing, and it's a type of ice that can break off in the airstream and enter an engine intake. The common temperatures of rime icing are below -8 degrees Celsius. However, rime ice has been observed from -2 degrees Celsius to -28 degrees Celsius. And the most probable range is -10 to -20 degrees Celsius. The frequency of encountering rime ice is 72%. Clear ice is a relatively slow freezing of large supercooled water droplets. In this case, only part of the water droplet freezes upon impact, and the rest of it spreads out along the component. In that case, no air is trapped, so it's a very clear and glossy type of ice. Also, it's a faster accretion than the rime icing. Clear icing is most commonly found in cumulus clouds because cumulus clouds form due to updrafts, vertical air rising, and that type of motion can support a larger water droplet. It's also a relatively warm type of icing, usually found from 0 degrees Celsius to minus 10 degrees Celsius, although clear icing has been observed as cold as minus 25 degrees Celsius. Mixed icing is a combination of clear and rime, found in a temperature range from minus 10 degrees Celsius to minus 15 degrees Celsius. Clear ice is encountered 10% of the time, whereas mixed icing is encountered 17%. Let's consider the distribution of icing zones in the atmosphere. 85% of all icing conditions are associated with fronts, cold fronts and warm fronts. In general, cold fronts have a very narrow icing zone. The icing encountered in a cold front is faster accreting because usually clear icing and mixed icing is encountered, and also more intense. The icing intensity is greatest immediately above the frontal zone, and cumuliform clouds within 100 miles to the rear of the cold front in that cold dense air are icing hazard areas. Extensive layers of stratocumulus at the surface position and to the rear of the cold front is also an area of icing hazard. The vertical extent of those clouds depends upon the stability of the warm air mass. As that cold air pushes that warm air, and clouds and the warm air are lifted up the front, if the warm air is unstable, it's going to be lifted to a greater level, possibly higher than 30,000 feet. Icing is not usually encountered above that level, but has been encountered as high as 40,000 feet in those type of cumulonimbus clouds. A warm front, in contrast, is more of a stratified cloud system. A warm front has a more gentle slope than a cold front, as warm air is pushing along and rising above colder air. In that case, there's a greater horizontal extent to the cloudiness and to the icing hazard. In contrast to the cold front, it may be possible to climb out of the icing conditions up into the warmer air. The frontal inversion separates the warm air above from the colder air below. Rime icing is a hazard directly below that frontal inversion. Also, mixed icing within 100 to 200 miles in advance of that warm front have also been observed. Rime icing may be common up to 300 miles in advance of that surface position of the front, usually associated with altostratus clouds. Clear icing is a hazard where freezing rain falls out of the warmer air above the frontal inversion, and that rain is freezing in the cold air. Again, if the warm mass is unstable, then the type of clouds associated with the front will be more of the cumuliform variety, and clear icing will be present in addition to the rime and mixed already mentioned. In preparation for a flight, NATC requires that you receive some weather information. Let's talk about that next. For local VFR flights, it's a common practice in TAC Air to get your weather information off the weather vision. The problem with that is that you won't have all the information you need to take evasive action if icing is encountered in flight. Again, remember, your reaction time may be severely limited. So you're encouraged, if icing is going to be a flight hazard, to obtain a face-to-face flight weather briefing with a DD 175-1 flight weather briefing form completed. Navy forecasts are based on the current and forecasted upper air winds and temperatures, dew point spreads, in consideration of precipitation, frontal, orographic lifting, and cloud type. Before we go any further, let's talk about the 5 factors which affect icing on aircraft. I've talked about them in different forms already. The first 3 are meteorological factors: temperature, liquid water content, and droplet size. The other 2 are aerodynamic factors, which will be addressed after my talk: collection efficiency and aerodynamic heating. To obtain a complete icing intensity forecast, a forecaster needs to know all 5 parameters. Navy forecasters are proficient in the meteorological factors. However, may not be totally knowledgeable of the aerodynamic factors. So it's important for you as a pilot to be aggressive in receiving your icing intensity forecast. For example, some general procedures to follow are to locate areas of probable icing at your flight level on the up air analyses maps. In order to do that, look for upper analyses stations that have shaded in areas. Those are dew point spreads of 5 degrees or less. Locate dew point spreads of 3 degrees or less in conjunction with freezing temperatures 2 degrees Celsius to minus 20. Those are areas of probable icing depending on the aerodynamical factors. In addition, on the prognostic charts, look for warm, moist air that may be flowing from oceanic or lake areas over land where it may be lifted by either front or by terrain. In orographic lifting, wave clouds form on the windward side of a mountain as warm, moist air is lifted and the moisture condenses into clouds. If the freezing level is below or in that cloud level, that's a very serious ice hazard. You're advised not to fly below 5,000 feet AGL over mountainous terrain in those situations. Consider also that ice clouds, such as cirrus, are not an icing hazard because ice does not usually adhere to an aircraft. There may be some suspended supercooled water droplets in a cumulonimbus cloud at higher levels, but cirrus clouds, such as jet stream cirrus, are not a hazard. Finally, plan evasive action. Know where that warm air is. Know, for example, that in a warm front you may be able to climb in the warmer air. However, in a cold front, climbing would put you in a cumulonimbus cloud, for example, up to levels of 30,000 feet, which would be very dangerous. In that case, a 180 may be your best evasive action. That concludes the meteorological factors in aircraft icing. I'll introduce now Brian Picard, who will talk about the aerodynamical factors involved.
Thanks, Jim. Now that you have a better understanding of how ice is created and encountered, the next step will be to explain why ice formation on the surface of an aircraft is a serious flight hazard and why the newer jets especially are much more susceptible to ice accumulation and the problems that are associated with it. The rate and extent that ice accumulates on any particular aircraft surface is dependent on many things, but to a greater extent, the aircraft's speed, the size of the water droplets, and the size and shape of the moving surface. Based on that information, the term collection efficiency can be used to define how susceptible a particular aircraft surface is to ice accumulation. Take, for example, an object moving through the air. Its movement disturbs the pressure field around it, which results in a pressure wave moving out ahead of the surface. The airflow warned by this pressure disturbance parts and flows smoothly around the disturbing object. The cloud droplets also try to make the turn along with the airflow, and in general, the small ones tend to follow the airflow streamlines, whereas the larger ones tend to fall out and impact the surface. The collection efficiency can be defined as the ratio of the amount of ice a surface does collect to the amount it would collect if every droplet in its path hit the surface. With that, we can conclude that those components having large radii of curvature deflect a larger percentage of the water droplets, especially the small ones, whereas those components having small radii of curvature deform the airflow less, resulting in a larger portion of the water droplets hitting the surface. This should explain why today's fighter-type aircraft, with their sleeker, more aerodynamically efficient forms, have much higher collection efficiencies as opposed to the older, larger, bulkier aircraft, such as the F-4s, the F-14s, the A-6s, and especially the cargo transport aircraft like a C-130. Now, the most common problems with icing that we're familiar with are the penalties of weight and drag, the reduction in lift, and of course the resultant increase in stall speed. These penalties become much more serious with today's newer jets. The way in which ice accumulates on the leading edge of a wing, for example, is probably different from what you might first initially imagine. In general, ice forms around the stagnation point and grows outward, and in some cases results in a horn-shaped cross-section, which can obviously seriously affect the aerodynamic effectiveness of a wing. With this in mind, and remembering that the collection efficiency is much higher on thinner surfaces, such as the leading edge of a thin wing, you should be able to figure out why even a small amount of ice accumulation could drastically alter the airflow around the wing and dangerously affect the aerodynamic effectiveness. Now, the engine intake, and more specifically the inlet lip, is the other major area of concern. Inlet lips are generally very thin, making their collection efficiencies very high. The probability of ingesting ice from the inlet lip is primarily dependent on the amount of inlet spillage present. Inlet spillage occurs as a result of more ram air entering the inlet than the engine can use, which results in back pressure at the inlet face, causing air to spill out the sides of the inlet. Although inlet spillage represents an increase in aircraft drag, it helps to eject ice on the inlet lips outside of the inlet, eliminating the hazard of ice ingestion. Unfortunately, modern technology has provided a more precise match between the engines and the inlets, which in turn reduces the amount of inlet spillage and ends up increasing your probability of ingesting ice from the inlet lip. There have been several advances in engine technology as well that have increased the engine FOD probability. Engine FOD tolerance has been significantly decreased with the use of lighter, less structurally durable material throughout the engine in an effort to increase the thrust-to-weight ratio and the development of thinner, more aerodynamically efficient fan blades. Modern engines, such as the F404, which powers many new technology fighters, such as the F-18, the F-20, and the upcoming A-6F, for example, rotates at compressor speeds approximately 30% higher than a J-52, an older engine with essentially the same compressor diameter. Now, that increase in speed equates to an increase of approximately 60% in the kinetic energy exchange between the ingested ice and the compressor blades. And as a result, that, coupled with the low blade FOD tolerance, results in a very high probability of engine damage. As an example of how serious icing can be on our modern jets, we'll summarize the results of the icing tests conducted for the F-A-18 Hornet, the Navy's newest multi-mission jet. Most jets are subjected to icing demonstration tests early in their acceptance programs, which in most cases requires the use of an artificially generated icing cloud provided by the Air Force NKC-135 water spray tanker. In this particular case, an F-18 was flown for 7.5 minutes in a cloud which had a liquid water content of only 0.5 gram per cubic meter, which was considered to be only light to moderate icing. For visual purposes, the water in the tanker was dyed yellow to make it more apparent as it accumulated on the aircraft surface. In that time frame, the leading edge of the wing and the inlet lip accumulated rime ice very rapidly to about 1/2 inch, primarily because of their high collection efficiencies. The aircraft radome, canopy, and the bottom of the aircraft, because of their low collection efficiencies, began to accumulate ice as well, but at a much reduced rate. It was only considered to be trace ice. The leading edge extension accreted ice at a rate between that of the radome and the inlet, measuring about 1/8 of an inch at the end of the icing sequence. That ice generally shed in small pieces over the top of the Lex, creating no fault hazard. The test had to be terminated after the ice accumulation on the inlet lip was ingested into the engine at about military power. The ingested ice resulted in an immediate compressor stall, which luckily cleared at flight idle, but was found to be unusable for higher power settings. For comparison, earlier tests were conducted for lower power settings, which resulted in a similar amount of ice on the inlet shedding outside of the inlet as a result of inlet spillage, and thereby reducing the possibility of damage to the engine. After the F-18 landed, the engine was inspected and was found to have sustained major engine damage. All of the first stage fan blades were either curled forward, torn, or missing pieces. And all this from only a ½ inch ice accumulation on the inlet lip. Those results clearly demonstrate one of the very real hazards today's fighters are faced with, and the reason why all pilots must develop an awareness of the dangers present if ice is allowed to accumulate on the aircraft, and especially the inlets. This concludes my portion of the brief, and now I'd like to turn over the remainder of the brief to Major Rick Shows.
Obviously, the most important precaution a pilot can take would be to avoid any meteorological conditions which constitutes a potential icing environment. If flight into an icing environment is anticipated along a flight plan, the best thing a pilot can do is to establish an alternate flight plan around the problem area by changing altitude and/or course. In some cases, however, penetration into icing conditions is unavoidable. If that's the case, a pilot should attempt to determine the type of cloud he will be entering, determine the icing severity by consulting available PIREPs, and establish a descent technique. Knowing what type of cloud you are about to enter will provide critical information for escape if severe icing is encountered. For example, if you are in a stratus cloud, you know that they are typically around 3,000 to 4,000 feet thick, with a maximum vertical extent, if layered, of 6,000 feet. So a change in altitude should get you out if a severe icing is encountered. A cumulus cloud, on the other hand, has great vertical extent over a much shorter distance. A change in heading may get you out of that problem area. Avoid, if at all possible, penetration into a wave cloud. This type of cloud is easily identified from above because it looks as its name implies, like a series of waves, and as explained earlier, are created over mountainous regimes. Prior to encountering the cloud, you can determine if the cloud is composed of liquid water droplets or ice crystals. Take a look in the direction opposite the sun, down onto the clouds where the aircraft shadow would be. If you see a colored ring around your shadow, or instead of your shadow, the cloud is liquid, and if the temperature down there is right, a potential icing hazard may exist. Now look towards the sun, again down at the cloud tops. If you see a brilliant spot of light, not colored, you are looking at a reflection from ice crystals. This should tell you that at least the top portion of the cloud is not liquid. If penetration into a known or suspected icing cloud is unavoidable, enter the cloud at the last possible moment and go through it by the shortest possible route, either horizontally, vertically, or both, depending on the type of cloud. Penetrating the cloud at an airspeed providing an aircraft total temperature of at least 5 degrees Celsius should protect the wing leading edges and inlet lips to some degree as a result of aerodynamic heating. Many modern cockpit displays are equipped to read either aircraft or inlet total temperature or ambient temperature, from which total temperature can be derived. As an example, a pilot encountering icing conditions at 5,000 feet would have to accelerate to 425 knots for an ambient temperature of minus 20 degrees Celsius, 330 knots for an ambient temperature of minus 10 degrees Celsius, or only 215 knots for an ambient temperature of 0 degrees Celsius, to provide an aircraft total temperature of at least 5 degrees Celsius, which are airspeeds well within the performance capability of a tactical fighter. The pilot should attempt to maintain constant throttle settings and reduce speed to transition for landing at the last possible moment so that gear ice will be minimized. If for some reason airspeed cannot be adjusted to prevent ice accumulation on the inlets and wings, the throttles should be reduced to the minimum practical setting in an effort to induce inlet spillage and result in inlet lip ice shedding outside of the inlet. If the aircraft is carrier-based and a wave-off is signaled, the pilot should use the minimum power required for a safe wave-off and clean up as soon as possible to reduce any additional ice accumulation on the landing gear. On the other hand, if you find yourself already in a cloud and icing has begun, accelerate to provide the desired total temperature, 5 degrees C, and climb or descend out of the icing environment. If time and fuel permit, attempt to climb to a safe altitude. Altitudes above approximately 25,000 feet and ambient temperatures below minus 30 degrees Celsius are generally free of icing due to cloud glaciation. Descend only if you are sure that the ambient temperature is well above freezing at a safe altitude below. Remember that sooner or later you will have to descend through it, but there is no reason to rush the descent if unsure of the conditions below. Just about all modern aircraft are now equipped with inlet ice detectors. In many cases, this will give the pilot advance warning that aircraft icing is occurring and that immediate action should be taken to avoid further accumulation. Remember that for many jets, the most critical ice accumulating surfaces, the inlets, are not visible by the pilot. And although very little ice may be visible on the exterior surfaces, a lot of ice could be building up on the inlet lips. In summary, reducing the possibility of an inlet icing incident is largely dependent on the pilot's knowledge of icing characteristics and avoidance. Taking some simple, necessary steps prior to and during flight can swing the odds of avoiding an incident in your favor. Remember, number one, if icing is suspected or anticipated along your intended flight path, conduct a face-to-face briefing with the weather office to find potential icing areas and file a flight plan which will keep you out of the danger zones. Second, if penetration is unavoidable, identify the cloud type from above and whether it's liquid or ice. Number three, consult the PIREPs and take into account your aircraft type and speed. Number four, establish a descent technique such as entering the cloud at the last possible moment at a speed providing plus 5 degrees Celsius total temperature. And if ice continues to form or is already present, reduce power during the descent to induce inlet spillage. The bottom line is that on modern tactical aircraft, icing rapidly degrades aircraft performance potential and compromises flight safety. It's up to you, the pilot, to realize the potential safety hazard you can be faced with and know how to decrease the odds of an in-flight incident through an increased awareness of understanding of icing avoidance. Thank you very much for your time.